Hello everyone, hopefully you're doing well. In this video, we're going to take a look on chapter 10, modeling with geometry. The first sections we would, really review the fundamentals of the geometry. As you probably learned from your previous class, mathematics class, or from algebra, also we talked a little bit about geometry. The word geometry literally means earth measure because many ancient cultures developed geometry and geometrical methods to survey flood basins around agricultural fields and to establish patterns of planetary and star motions. However, geometry was always more than just a practical science, as we can see from the use of geometric shapes and patterns in ancient art. So the Greek mathematicians, probably that's the one you heard a lot, Euclid, summarized Greek knowledge of geometry in a 13-volume textbook that's called Elements. So the geometry described in Euclid's works, now called Euclidean geometry, is the familiar geometry of lines, angles, and planes. In fact, when we hear the word geometry by itself, we generally assume that it refers to Euclidean geometry. So that's what we're going to do in this particular unit, the fundamentals of geometry. We'll explore the foundations of Euclidean geometry. So we would see spatially geometric objects such as points, lines, and planes that represent idealizations that do not exist in the real world. So a geometric point is imagined to have zero size, right? Um, so no real object has zero size, but many real phenomenon approximate geometric points. Stars, for example, appear to our eyes as points of lights in the night sky. So when you have only one point, it's also geometry. Okay, so a geometric line is formed by connecting two dots along the shortest possible path. Okay. It has infinite length and no thickness because no physical object is infinite in length. Very important. So you can see you can continue indefinitely in both directions for that. But of course, at some point, we usually work with a line segment or a piece of line. A line, a line segment or a piece of lines. It's a long taut wire. Uh, you know. Um, is a good approximate to a line segment. So a line segment, if we have, oops, nope, this in 2 point A and B like this, we can call it a line segment. So a line itself is this one. All right. So, or we can say line segments, one side is continue indefinitely. So we can go like this because otherwise we're gonna have a ray also, very important. A geometric plane, that's the last one, is perfectly flat surface that has infinite length and width. Um, but no thickness. A smooth tabletop is a good approximation to a portion of plane. So we have different ways of seeing things. The same way we can describe, uh, you know, like dimension of an object can be thought as the number of independent directions in which you could move if you were if you were on the objects, right? So, if you were confined to a point, you would have no place to go. So, a point has zero dimensions, so we need to remember that. Um, you know, a line is one dimensional because if you walk on a line, you can move forward and backward along only one path. Okay, so very important because we have the line. One coordinates locates on a point of on a line because coordinates is something we need to think about. So if we think also about dimensions instead of the number of coordinates required to locate a point, a line is a one-dimensional because it requires only one coordinate, such as x, to locate a point on the line, right? So we can also have a plane is also two-dimensional because it requires two coordinates, as you can see, uh, on a XY plane. So that's required in X coordinate and a Y coordinate. So we said X coordinate and Y coordinate. So you require two of these. Okay, so that's a plane. A line is a one dimension. We got only one coordinate, but a plane is two dimensional because it requires two coordinates to locate a point on a plane. Remember, a point has two coordinates, has an x coordinate and a y coordinate for a two-dimensional plane. Three coordinates such as x, y, z, right there. This one has XY. This has only X, and this one has X, Y, and Z. So we are in a three dimension. Of course, that's something you can verify. Three coordinates such as X, Y, Z are needed to locate a point in a three-dimensional space. So very important to verify these three, whether we use only one coordinate, two coordinates, or three coordinates. So we're gonna need these for further explanation in mathematics. But also, one of the very important geometric objects we need to talk about is the angles. So the intersection of two lines or line segments forms an angle. For example, let's say the intersection, if I have a line going this way and another line going that way, as you can see, this is the intersection that's going to form an angle. I can say theta is an angle, right? So we call it an angle. So in terms of angles, we have different ones, right? The point of intersection is called also the vertex. So any type of the vertex is everywhere. It's, where two lines intersect. So let's say if we said this is the angles here, this point right here, we can call it vertex also. So sorry, I need to erase. Oops. Okay, I'm hoping that's right. Okay, I'm gonna erase it. Okay, that's right. So we said if we have a line and another one going like this, we can create an angle. So that's one example of angle, but angles can also be in this way, or angle can also be very straight. So and then let's consider this one as also as an angle, or angle can also be, we can have angle different ways. An angle can be the other way around as well. That's also can be an angle. So we said that because the point, the intersection of two lines or line segments from an angle, the point of intersection is also called the vertex. So how many different angles we can have? Remember, a circle, what is the total measurement of a circle? A total measurement of a circle is 360 degrees, right? So 360 degrees. If you take any circles, I'm gonna take a circles like let me insert a circle to make it much easier for us to work with. If I use a circle like this, okay, so let's second is that circles I would consider it's not filled up. We're gonna just take this circle like this with a big giant color to make sure we get it. All right. So these circles, if I want to divide this circle into four equal parts, remember the X, Y, Z, we know each quadrant here is 90 degrees. So a 90 degrees is a very right angle. So because we can do like this, if you can do something like this, very straight. So we know that angle is 90 degrees. We call it right angles. So straight angle is 180 degrees. So 90 degrees plus 90 degrees, that make it 180 degrees. So in this case, if we do that, it's gonna be something, So when we do that, this one is 180, 90 plus 90. But acute angle is any angle, that angle right here, let's call this angle theta. So theta is less than 90 degrees, right? So an obtuse angle is an angle that is between 90 degrees and 180 degrees. We call it an obtuse. So straight angle, as we said, if we call this one theta, that straight angle is really equal 180 degrees. And right angles, if I call that angle theta, so we know right angle theta is uh, equal to 90 degrees. So acute angle is an angle that is less than 90 degrees. Usually we start from the x-axis positive, when you have a horizontal line that we call it x-axis. So because we move from right to left, counterclockwise. So we know to create the angle positive, we're going to move counterclockwise. But if, of course, if we want it to be negative, this is, for example, a positive angle. So if I have this one, let's suppose this angle here can be 60 degrees, an examples, right? But the same way, I can have another angles like this one. Let's say maybe this angles here, I can say it's theta is negative 50 degrees, all right? So here theta is 60 degrees. So different ways of explaining the angles. All right. So I think we're ready to do a few examples here, and of course you're gonna enjoy. Let's go very quick on different examples. The first examples we have, find the degree measures of the angles that correspond to each of the following parts of a circle. So remember, we said a circle is a total degree of a circle. If you take a circle, the total is 360 degrees. Now they said find the degree measures. So if you take half of a circle, what half of a circle represents in terms of degrees? The measures in degrees, because a circle can be measured either in radians, 2 pi, for example, or it's 360 degrees, or 2 pi. If you use degree, you use 360. If you use radians, it's going to be 2 pi. Now, half of a circle will represent what? No, if you want half a circle, all you need to do is half times 360 degrees. What is half of 360 degrees? That is 180 degrees. If you have 1/6, all you need to do 1/6 of mean multiplication degrees. So 360 divided by 6, that give you 60 degrees, right? If you have 1/5 of a circle, 1/5 of a circle, just multiply 360 divided by 5. What is, in this case, we do 1/5 of a, we're gonna do 1/5 of a circle. If I take, you know, the if I divide 1/5 of a circle, I'm gonna find 72. Okay, 72 degrees. Two-thirds of a circle, I need to multiply two-thirds by 360 degrees. So that will be 2 times 360 over 3. Of course, you can verify that multiple times to make sure you remember how to do it. Two-thirds would be 240 degrees. All right. So you see those fractions give us something less than 360 because the numerator of each fraction is less than the denominator. So it's a proper fractions. All right. So that's the first examples. We can also do and a few other examples where they would ask us to find the fractions of a circle corresponding to each angle. So what is the fractions? Because in this case, it would be different what they ask us to do here. So we said 45 degrees, find the fraction of a circle corresponding to each angle, right? So 45 degrees would be 45 over 360 degrees. You just need to divide. All right. So when they ask you to do these type of studies, it's really doing some conversions, which should be fine, right? Now, what we do, 300, I mean 45 degrees divided by 360, of course, that would give you 1/8. We may only simplify because 45, okay, how many 45 you have in 360? That's it. All right. So for us, if you have, because the top part would be 45 times 1, and, or we can say 1 times 45 degrees. Okay. If I grab my calculator, I can see clearly, if we take 360 divided by 45, it gives us 8. So that means 8 times 45. When you cancel these two, you have only 1/8 less. So that's how you need to do each of them. You do 6 over 360. 6 over 360 would be 1 over 60. So you can 1 over 60 for this one. If you have 300 over 360, so if you do 300 over 360, that will give you 5 over 6. So I hope you can use these examples to do more exercises at some point because next topics would be about really introducing the plane geometric. So plane geometric plane geometric is the geometric of two-dimensional objects. uh, you know, uh, we can examine features of circles, polygons. Circle and polygons. I don't know if polygons means you have different size. It's different size on your shapes. They are the most common two-dimensional objects. So all points on a circle have the same distance, right? All points on a circle has the same distance, the radius from the circle center. So if you have a circle and you identify the center, it doesn't matter where you're gonna go. So we know from the center everywhere you go, the distance will be the same. That we're going to call it radius. The diameter of a circle is twice the radius. So when I have a circle, remember, if I take it only from the center to any side, we call it radius, R for radius. But the same circle, instead of going if I go both sides like this, so this line going forward to the center. You must make sure this line that touch 2 points on the circle on your circle going through the center, we know that's the diameter. So that means the diameter is two times the radius. So diameter is equal to two times the radius, right? Or we can say radius is diameter divided by two. So, it's either way you can find it. So the diameter of a circle is twice its radius, which means the diameter is the distance across the circle on a line passing through the center. You need to make sure it goes to the center. I think the other one before we move, I would change it because we're supposed to talk about the polygons also, because we said polygons and circles are the most common two-dimensional objects. So a polygon is in any closed shape in a plane made from straight line segments. So the word poly comes from a Greek word for many. So a polygon is many-sided figure, right? So a regular polygon is a polygon in which all the sides have the same length and all the interior angles are equals, right? So we give you a few of these polygons, some very common regular polygons in the names. You can see table 10.1 give you the equilateral triangle, all the sides are the same. The square, all the sides are the same. Regular pentagon, all the sides are the same. It's like the size of the Pentagon in Washington or the size of France and the shapes of France. Regular hexagon, no, sorry, France is regular hexagon, not pentagon, so hexagon. So regular octagon and regular decagon. So all those shapes of polygons, the size are the same for each shape. Okay, so very important to remember. Of course, we're gonna have a chance to talk about triangles also, but I'd like to go back to some shapes. If they ask you to find the area again, for some reasons, I'm not sure we covered this exercise yet. Let me see where. Of course, I don't know why I put this exercise over there. So let me move it to its correct place so you know where to put it. All right. So I apologize for that. It's better we talk about triangles also. We said that polygon and circles are the most common two-dimensional objects, and you understand circle is a really round shape with a center and a radius or diameter. Polygon, so is in you know is in any closed shape in the plane made from straight lines. So triangle are among the most important of all polygons, and they take many different forms. So all three sides of an equilateral triangles have equal length. Okay. So making it a regular polygon. So an isosceles triangle has exactly um and it has exactly two sides of equal length. So we have the isosceles right here. Two lengths are the same. All right, equilateral, all sides are the same. Isosceles, two sides are the same. A right triangle, this is a right triangle, both of them right triangle, because usually to show it's right triangle, we put that symbols, right? So we said it's a right triangle contains one right angle. So because we know here the right angle is 90 degrees. 90 degrees. Remember, when you add all the angles on a, let's say for an angle, for this one, for example, if you add these three angles, each of them would be 60 degrees because they are all the same, right? So because the total angles inside of a triangles. If you add all the angles, they should be equal to 180. So if I have any triangle, if I have angle A, B, and C, if I add these three angles, it must be equal to 180 degrees. So that's the three angles you have for triangle. So right triangle contain a right angle. I think we will return to right triangles and the many use later, right? Because we're gonna sketch some triangles, particularly triangles with one very large angles and two very small angles. So we can probably convince yourself that all triangles have the same property like these three, right? The sum of the three angles measures, as always, 180 degrees. So that's exactly what we said here. We're gonna sketch it. Another things we need to learn about is the perimeter and area. All the shapes we just talked about, either circle, polygons, triangles is one of different polygons we have. Remember, triangle is not one by itself. Triangle is part of the polygons, right? Polygons, we said that has more than one side, more than two sides. We call it polygons, right? But for these, you either need to know how to find perimeter or the area, but for circle, we don't call it perimeter, we call it circumference. So very important to remember this part as well. When we have to deal with it. So the perimeter, okay, of a plane object is simply the length of its outer edge, right? We can find the perimeter of a polygon by adding the lengths of the individual edge. So if you have a rectangle and you have length and width, if you want to find the perimeter, all you need to do, you add up everything. So L plus, if we said perimeter equal L plus W, that would be the perimeter, right? The perimeter of a circle, we call it circumference. And there is a different formula for it. Of course, we're going to have a chance to see it. We can find the areas because areas would be a little bit different. Remember perimeter. Let me explain what perimeter means. If I have a yard and I want to build a fence around my yard, okay, suppose my yard has a rectangular shape. If I want to build a fence around that yard, I need to know the perimeter. When I go to the store, they would ask me how many feet do I need? Because they would say they know I need length, width, so that's perimeter. But we can find the areas of many geometrical objects with fairly simple formulas. Because the area, when we talked about the area, if I have a yard, to build a fence around that yard, I need the perimeter. But if I want to put grass on that yard, I need the area. So area is very important. It's like if you want to put rugs in your bedroom, so you need the area. Okay, very important. So we have some shapes, okay, and formulas, perimeter and area formulas for familiar two dimensionals. Circle, usually, as we said, from the center, you can find the radius or this. But remember, we don't call it perimeter for a circle. We call it circumference. Is 2 pi r. We prefer to use 2 pi r, and the area is pi r squared, so we call it A equal pi r squared. Those are formulas. If you have a square, all sides, to find the area, you just do the area for us is L times L, but many people would call it S for sides. That means L square. But for the perimeter, we need to add all the L's together because we add all the sides that give you 4L. Now the rectangle, adding the perimeter would be L plus W plus W. That give you 2L plus 2W. Okay? But for the area, it will be length times width. All right? So we give you the parallelogram, the triangle for both perimeter and the area. Well, let's put A for area, P for perimeter. So now you know at least a few of the two-dimensional objects, how to find the formula we can use to find the perimeter and the area. Let's go over one or two examples very quick because in these examples they ask us to find the perimeter, the circumference, and the area of each circle. Oh, those are all about circles. I thought we had some other ones, but you know what? We're gonna do only circles in this case. All right. So the first one is circle with a radius. I mean, for us, R equals 6 because we said circle. If they ask us to find the circumference we know is 2 pi r. So that means 2 pi times 6. That gives us 12 pi. It's better we leave it like this. Or because you know what is pi. What is pi again? Numerical value for pi? 3.14. Of course, we can say 3.141595326, etc. We have 22 trillion digits of pi, but we're gonna use only the 3.14. So when you multiply this, it would give you 37.7 feet because we're dealing with feet. That would be the circumference. But if you want the area, remember for a circle is pi r squared. So we're gonna have 3.14 times r 6 square. What is 6 square? 3.14 times 6 square. That would give us 113.1 square feet. Remember, that should be square feet. Square units for area, just the unit for perimeter or circumference. Okay. Now, we can do one with diameter now. Let's do C. For C, this is the circle with a diameter. Remember, diameter, if I have D is 2R. So meaning circumference, we can say 2 pi R, or we can say circumference is pi D when we know pi D when you know the diameter. Now, let's go. We have the circumference equal pi D because we know the diameter for C, D is 23. Okay, so we're gonna have 3.14 times 23. Of course, if you use a calculator for this one, uh, right, we're gonna have 72.3. 72.3 feet. Okay. Now, if we go for the area is because we know, remember, area is pi r squared. But remember, what is r when you know the diameter? Because the diameter is 2r, so r is diameter over 2. So if we want to rewrite this one, we can say pi d over 2 square. So it's gonna be pi d square over 4. That's the formula we're gonna use to find the area. So what we do, so in this case, pi d square, d is 23, power 2 over 4. So when you do that, you obtain 415.5 square feet. Remember square feet for the area. Very, very important. We have a bunch of examples we could do because here I change a little bit the type of exercises we're planning on doing. I do a few on circles. Now we said find the perimeter and area of each figure. You can round. Remember A, for example, they ask you perimeter of a square because this is very that's a square. So that means all these sides are the same. All right. So for this, the area, the perimeter would be you add all the sides, 8 plus 8, or you just say 4L. Okay. Remember we said it's a 4L. I mean 4 times 8 is 32 miles, right? That's the perimeter for this one. But they ask you also to find the area. Remember the area for that one is L times L. That means 8 times 8. That gives you 64 square miles. We said square miles because it's area. Another examples with for rectangles, we can do a rectangles. Remember, for a rectangles, we need to have a width and a length. So the length in this case, they said is 8, and the width is 4. That means the widths are the same because it's a rectangle. And we know for perimeter, you need to add all of them. That means 8 plus 8 plus 4 plus 4. When you add 8 plus 8 plus 4 plus 4, that gives you 24 inches. But for the area of a rectangle, the formula is length times width. Okay? So if you have the area of a rectangle is length times width. So what you need to do, you do 8 times 4, that gives you 32 square inches. All right. But parallelogram would be a little bit different because, in terms of shapes also, you need to learn how to construct a parallelogram. This is parallelogram at some point. I'm gonna just use a different color. Okay. For the parallelogram, approximativement, you have a base, you have a width, and remember, you must have a height. So that's a parallelogram because we have three different informations. A parallelogram with sides of length 8. Remember, you have the length and 30 feet of distance. You have the base. And 4 feet between the 30 feet. So that's the height, right? So we have the height. So for an examples like this one, because it's a parallelogram, formula for it, we just need to multiply them, guys. So we said it's in terms of perimeter. Okay. So perimeter, this is the formula we have. If you go back here, what's the perimeter of a parallelogram? We said it's 2L plus 2W. Okay. So we have 2L plus 2W. That would be our parallelogram. Okay. So we have uh, 2 times 8. So we have 2 times 8 plus 2 times 30. Okay, so that's make it 18, no 16 plus 60. 16 plus 60, that make it 76 feet. That's a perimeter. But for the area of a parallelogram, let's go back to parallelogram. The area is length times height. Area would be length times height. So meaning area would be 4 times 30. Let's make it 120 square feet. Hmm? I hope these examples help you to do more in these sections, but in the meantime, we have a few problems that we can work with to make sure you really get what we cover in this. Here, a window consists of 4 foot by 6 foot. As you can see, that window right there has two sides. So first of all, we really have a rectangles from that window, right? That's a rectangle. We know the rectangle. That rectangle capped by a semicircle. So this is the semicircle. Remember, that's half of a circle. Well, actually, that's mine is not. But you have a rectangle, and you know the diameter here is d equal 4, right? Because it's the same thing like the width. How much trim is needed to go around uh, the window? So first of all, we need to do both. We need to split it into, first you have a rectangle, and that rectangle is 6 feet 4 feet. So the area, I mean, we no, how many trim is needed to go around it? So in this case, because we said it's gonna go around it, we're gonna I mean, don't pay attention to the top part, because the reason why you don't need to pay attention to the top part, because you're gonna put the semicircle to it. But let's say 666, so the perimeter in this case, right, the three straight edges have a total length of 6 plus 6 plus 4, that make it 16 feet, because we're gonna do it around. So the perimeter of the semicircle cap is half of its circumference. Remember, for the other parts, and we know D is 4, or if you want, you can say, because R is for would be 2 if you want to see it that way. And we know a semicircle is half of a circumference. What is the circumference? The circumference is 2 pi r over 2. So that means it's only pi r. So if it's pi r for that semicircle, the circumference would be pi times 2. That's 2 pi. Okay. So we have pi times 2. That make it 2 pi. So meaning that part would be 2 times 3.14. That is 6.3, right? Good. Now we have the total. You need to add both. Totals would be 16 feet plus 6.3 feet. Total would be 22.3 feet. So what do you need? The total length of trim needed for the window is about 22.3 feet. So you can go to the store and order it. So which is fine. I think that's a pretty good examples. But as we said, because we want to make sure you understand how to work the problems out, looking at this one, you see you have built a stairway in a new house and want to cover the space beneath the stairs with plywood. What is the area of this region? So for now, as you can see, if you want to reproduce this, it shows like you have a right triangle, right? If you agree, this is what we can see here is that we have a right triangle, but it's most of all because you have the height and you have the base. Now, what is the area of a triangle in this case? If you want to go back and take a look, area of a triangle is 1/2 base time height. So if you take the area, it says 1 times base time height. What is 1/2 of, the region to be covered is triangular, right? With a base 12, okay, feet and height 9 feet. Now, you just need to do 12 times 9 over 2. So that would give you 6 times 9. So what would be the area then? Those are type of problems you can find is 54. Remember, that should be square feet, not only feet. It's square feet. So the area of the region to be covered is 54 square feet, right? So hopefully you like these problems because otherwise I'm gonna look at it by myself and I really want to share this with you and hopefully you would follow. Now, you see so much about two dimensionals. How about the three-dimensional geometry? So two of the most important properties of three-dimensional objects such as box or a sphere are its volume and its surface area, right? So we have a table here that's give the names of several three-dimensional objects along with their volumes and area, right? So these tables right there give us some, very important. For example, the volume formula for a box or a cube is just the familiar length times width times height, right? So that would be the area of a rectangular box. Length times width times height. So all I need to do, remember this is the volume equal V equal. So remember volumes is cubic feet and the area, and area, right? So very important for this. The surface area for a box or a cube is the result of adding the areas of the 6 rectangular faces of the object. The volume formula for a cylinder should make sense to you because it is just the area of the circular basis pi r square multiplied by the height, right? H. The surface area for a cylinder has two parts. The area of each circular end of the cylinder is pi r squared. So the area of the curved surface of the cylinder is found by using a correct trick so that you would see later, very important. Now, let's practice it in one or two examples. Let's say in this situation, you know, we're gonna try anyway, right? Let's try it. A water reservoir has a rectangular basis that measures 30 meters by 40 meters and vertical walls 10 meters. Remember rectangular, so we have all three. We have the length, we have the width, and we have the height. Remember the vertical, that's the height. Okay, we have that's the length and that's the width. Okay, it was filled to capacity. At the end of the summer, the water depth was 4 meters. How much water was used? Yeah, I know for this one, volume of the water at the beginning, so you can find it very quick because volume of the water at the beginning. Because at the beginning, we know the formula to find it because volume is length times width times height. So that volume right there would be 30 times 40 times 15. So the volume would be at the beginning would be 18,000 cubic meter. Remember, it's cubic. That's the water we have at the beginning. But you know what? Because they said that now at the end of the summer, the water depth was 4 meters. So this is the new height, right? So the height at the beginning was 15. Now the new height is 4. All you need, we're gonna keep the 30 and 40, but except change the 15. So because that would give you the volume of water remain remaining at the end of the summer. Okay? So we keep the length, the width, but the height change. So that's, remember, they are all in meters, 4,800 cubic meter left. So we said the amount used was how much, because they said how much water was used. So remember, at the beginning we have 18,000. So at the end we have 4,800. So the amount used was what you have at the beginning minus what you have at the end, what you have left at the end. So they use 13,200 cubic meter. Okay. 13,200 cubic meter. That's what you're gonna have at the end. Okay. That's very, very, very important. Okay. Very, very, very important. Okay. That's very important. Okay. Let's see. If we have any more examples to cover, because we have a few of these. We said another examples we can do. I think I'm gonna just do one of them and leave you to enjoy the other examples because it's very important for you also to try some on your own. We said a competition swimming pool is 50-meter long. So we have the length 50 meter and the width is 30 meter and the height is 2.5 meters. So we said how much water does the meter? I mean the volume, right? What is the volume? And in this case, we have a feeling the volume is only length times width times height. So meaning 50 times 30 times 2.5, and you're gonna find the amount of cubic meters, which is 3,750 cubic meter of water in the pool, right? I don't know if you can see it, but that's very important. We do this. For the next examples, where they ask you a grain storage building, is a hemispherical shell. Okay. All right, I'm gonna do this one like this. Okay. Let's do it. We said a great shell with a radius. We have the radius equal 25. You know, they said it is hemispheric. You know, sphere. It's like sphere. Hemispheric sphere. That's a radius. What is the volume of the building? So for hemispheric, we know the volume for a sphere. Volume of a sphere is 4 pi r cubed over 3. Right? This is the volume. Once you know what it is, you can do it. Right? But they said, what is the volume of the building? A grain built is a spheric shell with a radius. The building's volume is 4 pi r cube over 3. Yeah. So volume would be 4 pi. R is 25 power 3 over 3. Okay. Uh, but because it's the buildings, because the Egwene storage building is a spherical shell. So in this case, we're not gonna use all of it. So we need to make sure what we're gonna use half of it, right? Because we need to take half of it. So that would be one half of all of this. So meaning it would give you, when you do everything, it give you 32,725 cubic meter. Because it's the position of it. And they ask us also how much paint is needed to cover the area, the exterior of the building. So that means they want you to find the area, the surface area. Surface area of a sphere is 4 pi r square, but we're gonna just take half of it. Okay, so that's mean 4 pi 25 power 2 over 2. So the area would be 3927 square meter. Okay, so that would be what you need to cover the surface area. Um, to complete the five, because we need to really speak about, uh, you know, the five perfect solid. Plato formed ideas about geometry and the universe involving the five perfect solid. That's a long story that we could talked about, because that was another Plato's ideas about geometry and the universe involved the five perfect solid. Each of these perfect solid has the spatial property that all of its face are the same regular polygon. Plato believed that four of the perfect solids represent the four elements that the Greek thought made up the universe: the earth, water, fire, and air, right? So I don't know, the Dutch Cathedral, you believe, represent the universe as a whole, right? So we have all four triangles. As we said, the Dutch Cathedral, uh, you know, um, like this one. That's represent the universe as a whole. Plato presents his ideas in several of his dialogues. So in the dialogue, Timorous, in which he discussed the whole of the perfect solids in the universe, he also invented a moralistic tale about fictitious land called Atlantis. Interestingly, while Plato's ideas about the universe were abandoned long time ago, but millions of people today believe that Atlantis really exists. So Plato's fiction, in the end, has more adherents than the ideas in which he firmly believed. Commenting on this irony, the popular author Isaac Asimov, he even wrote a long sentence like, if there is, something. But you know what? Each of these perfect solids is such that all of its faces are the same regular polygon. So feel free to do more research on this, because scaling laws would be the next topics. As we saw earlier, scaling is the process by which a real object is modeled by a similar object whose dimensions are proportionally larger or smaller. So it's like you have a vehicle, so you can have the same SUV as a small vehicles, but in a different shapes. I mean, in a different dimensions. Scaling length laws, length scales with a scale factor, area scales with a square factor, and volumes with a cube of a scale factor. So feel free to come back and do these type of examples. Well, I'm gonna just do one of these for you, because I already do that a lot. Suppose you magically quadruple in size. That is, your height, width, and depth increase by a factor of 4. Right? By which factor would your arm length increase? Remember, this is something you need to think about that you do, and if it is so. For this one, what we would say your arm length has increasing by a factor of 4 because we said suppose you magically quadruple in size, that is your height, increase by a factor. So by what factor would your arm length increase? It would be increased by a factor of 4. You don't, that was it. They already said, right? B, by what factor would your waist size uh, um, increase? Again, your waist size is a measurement of length, so it will also increase by a factor of 4. Remember, it tells you, then you do it. All right, by what factor would the amount of material required for your clothes increase, right? So for this, the material required for your clothes is a function of surface area. So the amount needed has increased by a factor of 4 as well. So, 4 times 4, that's give you 16. Okay. So hoping this help. In a different video, we're going to come back with section unit 10B, problem solving with geometry. Take care. I'll see you in a different video.